Hi, this is a bit of an explanation into the Dino paper, which actually means distillation with no labels. So basically, Dino is actually a self-supervised learning method, and what makes it a bit attractive, or why it was a bit of a bigger change than the other self-supervised methods like, say, Swab or Moco or SimCLR, is because here they were actually not using any labels or negative pairs at all. So it was basically not using any labels or negative pairs, but somehow they had a student teacher method, which is something similar we have seen in distillation types, where they are trying to teach a student from a teacher, and somehow they are able to get very good results. The results are really good in the sense, like, if you visualize the self attention of the class token, you can see it's so good that it's almost looks like a segmentation mask. So the what they are showing is that if we do this method, like where we do a teacher student learning, which is something similar to distillation, we get very good representation. So now I will explain how they are attaining this good representation. So basically, their architecture, they're actually using a WIT, and they have the same teacher and student network. So maybe I can give a quick detour on what, say, distillation happens. So from Hinden's original distillation, how in Hinden's paper what it happened was, they have a big trained network, and we call it teacher, and there is we want a smaller network which is called student. So this is trained, and we train the output of students on uh, on the output of the teacher, as well as on the, so we give an image, we give it to both this network, we train it, we know the label, so we take the loss by combine loss from the output of, we compare the loss of our student with both the teacher and the label, and we say encode it with some lambda between them, and that's how it worked. So one thing to note here was this teacher network was trained, but here in Dino the teacher network is not trained. So here we initialize the student and teacher from the same state, and somehow, which I will tell, we are able to like they were able to train the teacher in a way to get good representation. So how are they doing it? So initially what happens is, they don't actually they don't actually do any actually gradient propagation in this side. So this is how this is an example where they pass in the image through both the teacher and student, and somehow uh, compare the outputs. So they compare the outputs with the cross entropy, but the thing is that they don't do a backprop on the teacher side. The backprop is actually happening on the student side, and how they carry over the weights to teacher side is through this EMA, moving average, exponentially moving average. So they, between cycles, they are actually moving the weights of the student to the teacher. So if so basically, in a top level manner, what happening is, they are passing the same an image. So this passing also have a bit of intricacies into it, but initially I will say, suppose they pass in, so this is your image, say, and you take a big crop which is 50% or more, and pass it through the teacher, and say you take a smaller crop and pass it to the student, and then you want the student to predict the distribution, what the teacher generates should be similar to that of the student. So basically you want the student to learn the distribution the teacher outputs, and after that, and you move an exponentially moving average of the student weights to the teacher. So this actually, from an intuition perspective, it should not work. The fact that this work is there are certain uh, problems that could the model can easily uh, by heart this and say output some same representation, so that this the teacher and student can output the same output. So how, so they also discuss about that in the paper. So what they say is they it's called mode collapse. So basically, what is mode collapse? So what they say is they do something called centering and sharpening that helps in avoiding this mode collapse. So what I meant by mode collapse is, suppose uh, it's easier, right? So the both the student and teacher can say the output is say 10 dimensional. Both the student can and teacher can output say, I'm going to say one is the main output and rest are same. So if both the student and teacher output something like this, then it's easier to fool the network, right? Then it will not be any learning any meaningful representation. What it will be learning, it will be something like this. So what centering does is, centering actually they keep a running average of the output uh, and subtract they keep the running average of the output and subtract it from the output of the teacher. So what do I mean by a running average? So it's basically the output, the final output logics. They keep a momentum based, or that's also an EMA based average. They keep it and subtract it. So what goodness can the subtracting? Suppose if my output becomes 1000, and later in the cycles also it becomes something like this. When I subtract, so this will be the uh, average, right? Because this my output is continuously outputting this. So but it's not good. Then my C becomes this. When I subtract C from my output, then my output becomes zero, all zero. Because now what happens when you do a softmax on this is become a uniform distribution, right? Everything is zero. So when you do softmax, it becomes a uniform distribution of, I don't know, 1 by 10, 1 by 10, 1 by 10, 1 by 10, since I'm assuming here as 10 as the output. So that's how centering helps. So how centering helps from mode collapse is, the centering actually push it to a uniform state. But pushing it to a uniform state is also not good, right? If both the networks are outputting a uniform distribution, say 1 by 10 all, I'm assuming the output will be 1 by 10. That is also good, not good. So how they prevent is by the normal softmax sharpening. So like, what is the softmax sharpening? So basically in sharpening, what happens is we have something we want to, in sharpening actually we are trying to push the other way. We want to push from a uniform distribution to even say if something is like 0.26 and something are very close by something like this, when we divide it by a term, say a short term, this become bigger, right? So actually this distribution, suppose, will be something like this this I mean, after sharpening, the distribution will peak around the value we divided by. The centering was actually trying to push it to a uniform scale, and sharpening is actually trying to push it to the other direction, not on a one hot scale. So these things are actually helping togetherly. These things are helping in such a way that the model is not outputting the same thing all the time. So this helps, they have found through the empirical study, or with having these two things actually help in having a getting a good representation and a, yeah. So they actually have a good graph explaining what will happen without centering and sharpening. Yeah, so this is the graph they have. So this is the target entropy. So here they show that if you don't do sharpening, like if you don't do sharpening, what will happen is your KL divergence will be 0. That is me. What that means is both the model and I'm just showing three outputs here. Both the teacher and student will output the same output, something like this. And if you don't do centering also, then the target entropy will be higher, but then also the KL divergence is 0. Then what happens is both are outputting the same output. I'm just using 1 by 3 here. I'm just saying 3 outputs, but when you see that when you use both of them, we are getting a proper entropy reduction from the target side, and the tail diversion is also not 0, but it's decreasing here. So this means that when you use both of them are important, and when you use both of them, we get a meaningful representation. Yeah, so now that you have understood why centering and sharpening happens, I will just explain it again what happens. So what happens is you get a patch. So I will explain why there is a different patch. So actually the patch, how you get the patch for the teacher and student is a bit different. So what the assumption is, like when you give teacher a bigger patch and you give student a smaller patch. So what they say is like this teacher patch from the original image, the teacher patch is 50% to 100%, and the student patch is 0 to 40%. So the student get a smaller patch and the teacher get a bigger patch. So the idea is the student should be able to, when it's learning something like that, the student should be able to say, suppose this is a dog or something like that, and when the teacher will be able to see the entire dog, and the student will be able to see only the legs of the dog or something like that. And by seeing the legs, and when they're trying to match the output distribution of the teacher, the student should somehow get meaningful representations, or figure out meaningful representations, as making sure that it is a dog. So that is how they do it. Yeah, so in the cropping, actually they do a 2:8 crop. So what I mean is, like, suppose you have some image, and this 50% crop is a center crop. So you will have 224 big crops, two big crops. What I mean is, like, these two big crops. So or I can explain it again. What I mean is, suppose you have an image, you will have two big crops and resize it to 224. So those I'm going to name it B1, B2, and you will have 8 small crops, say S1, S2 up to S8. So B1, B2, and S1, S2 up to S8. So you can actually, when you compare the student actually see, you can actually form comparison between everything, right? So what they do is they do this comparison between everything. So if you have 2 and 8, actually you can form 10 pairs and you can get 20 comparison, but they only do 18 comparison. What they don't do is they don't do the comparison between the same so the teacher only see the big batches, the student actually sees all the batches, and when they compare the output of student to the teacher, if this so the student actually have B1, B2 in each batch, they won't compare. When it's B1 and here B1, they won't do that. When it's here B1 and B2, they compare it. So actually only 18 comparisons happens. So the same when the same batch, they don't want to compare between the same batches. Not much learning can come from that. They want to compare it between the different crops. same crops are removed, so the teacher only see the 2 big crops and the students actually see the 10 crops. And when the crops are the same, like when the big crop, if the same, what are the two cases where it sees the same? It can be B1 or B2. Rest of the cases it compares, it can be compared. So that is what they show in this equation. So they have an equation, so this is that equation. So here they are showing exactly what I just explained. So this is PT, and this is P student. You can see that 2 big G is global crop x1 x2, and the student actually x naught is equal to x dash is for the teacher. It yeah, both cannot be the same. That is what they do there. And that's their loss is actually a simple cross entropy between them. So basically cross entropy is trying to learn the distribution similarly. Yeah, and how they update the weight is once they do the backprop through the, so you have to be careful here, like, because they don't actually do any backprop this is actually frozen, in the sense they don't backprop. There is no gradient accumulation in teacher. So what they do is they just copy the weights from the student to the teacher. So the assumption is this, it is much cleaner. So if you know the Polyak averaging, it's something they also mention about the Polyak averaging in this thing. So it's like when you do an STD here, it will be noisy, but if you do an Polyak averaging of the STD, the actual representation will be less noisy. So it's basically, if you do STD, it will go something like this, right? It can go like that, but if you're doing the average of those weights, it will go something like that. So that is what, yeah, you can read on Polyak averaging if you're interested. So that is why they do EMA. So here you should know that they do EMA twice, EMA at 2 places. So what are the places where they do EMA? So one place is here when they copy the weights. The other place is centering. So in centering also, they actually the output, they average the output, they take the mean of the output, and they do an EMA with the last mean. So actually EMA happens twice. In centering also is an EMA, and yeah, here the weight copying is also an EMA. So here you can see this is a centering. So as I said, centering is also an EMA. And one more thing that you have to know is, like, if you go into the what kind of architecture they use, they actually used a WIT here. They actually found through experimentation that WIT are great. So both the student and teacher are having the same architecture, but only the weights gradually differ because the teacher is a weighted average of the student. And another important detail they have is actually the output. The student both the networks have a linear output, a different Dino head. Let's call it Dino head. So you have a width backbone, and then you have a Dino head. So what is this Dino head doing? So what they are saying is, so this Dino layer is actually, after you go to all your encoder blocks of the width, finally you go to this Dino head where you have a 3-layer MLP. That is a simple MLP. And what after that is an interesting thing. So after the MLP, they actually uh, normalize. So you get your X from the bit, and then you pass it through the MLP, and this output they actually normalize it. So they L2 normalize it. So meaning by X by this, so they L2 normalize it. So why they L2 normalize is because now if you think about it, when you L2 normalize it, you can think about it as it's sitting on the, now all the outputs are sitting of same radius, right? After the L2 normalization, they are actually multiplying by a linear W. So this W is also special. I will come why that W is special is this W is also normalized W, in the sense like this W, the weight matrix, even though it's a linear layer, they will have this W actually normalized. So suppose so the W is normalized. So this X normalized and this W is normalized. What I mean is, like, you can in PyTorch you can use utils dot weight norm and pass in a nn dot linear. So it will be having the same number of parameters as nn dot linear plus a weight G. So what the weights, so all these elements in this weight matrix will be normalized by their weight. So the same kind of normalization will be happening here. So if I am saying W1 will be W1 by mod of W1, and when you multiply, so this is normalized and this is also normalized. So what happens is actually, so this becomes a cosine product. So that is what that is what the Dino head they want to leave. So they want this thing, the X to live on a sphere, in a high dimensional sphere. That's why they normalize it, and they want the similar features to align on them. So when you multiply in by the layer, in this way they observed that they were able to get a meaningful representation. They have actually the output. So here this X is coming somewhere around 256 or hidden to follow well to 2048, but yeah, so the basic idea is that, so they want this to learn on a cosine similarity. So they have the output Dino head designed like that, and this K is actually very high dimensional. K is something around 6556. So this is not, so the output logics are coming to this high dimensional layer. This is actually not any class or anything. So they empirically found that this dimension helps in splitting. So you can see, if X is 256 and the final output layer is 256 into K, whatever K is, you can see that it's a high dimension 256 dimensional sphere, and you are having some this K many points on the sphere. And so this similarly happens for the student as well, and then they compare the cross entropy between the sphere, between both of them, student and teacher, and they want to bring the stuff together so that the spheres align. So this is my explanation, so take it with a grain of salt, it might be wrong. They also have another thing, like in the teacher network, they freeze the teacher network over one epoch. They say that it works well. So now I will again explain the algorithm, and they have a snippet here in a bit more detail. So initially, as I said, they will augment, so they will get the actual data, then they will augment the data, and x1 x2, as I said, the augmentation will be there will be main big 2 x1 and 8 small x1 x2 and small s1 to s8 small chunks, and the student network is all the 10, but the teacher network only see 2, but they are just using it for an example here. So here you see the x1 and x2 of the student and x1 and x2 of the teacher. As I said, they don't compare the same stuff, so they compare t1 with s2 and t2 with s1, and they do a backward here. So after that, so this loss, we will come into the loss a bit detailed. That is the loss they have, and after they compute the backward, they update the parameter. So this is a teacher update happening through EMEA. So this is the EMEA or the Polyak averaging, and also this is the center averaging, which is also EMEA. So there is a couple of things happening here if you look into it. So we have the EMEA here. So one thing is like so this C is actually used in H. The C used in H is actually from the previous batch. So we actually update the C after the update. That is one important factor. They are also mentioned in the paper. So C for centering is used from the previous batch. Yeah, and this is so two places we have MEA. Now we will go into the loss. The loss is actually a simple cross entropy loss, but as I said, they do the centering of the teacher logits before centering and sharpening. So what is centering and sharpening? Centering is, as I said, is a basic subtraction of the C. So this is the centering part, and dividing by the temperature is the sharpening. So it's crazy that this is just a simple stuff and it works very so well. So then this is a simple cross entropy loss. So this is the basic algorithm. This is very simple to implement, and their implementation is open source, so it's very readable implementation. Also, they here have some details on the temperature set for student and teacher. The student is and teacher are different temperatures in the output logit side. So the student is having 0.1 and teacher is having a but lower. So teacher is a bit more sharper than the student. Now they have a ablation kind of study where they compare what is the actual important stuff. They found that if they remove the momentum averaging and momentum centering, then the loss actually becomes like the KNN. Like, so what do you mean by KNN and linear probe is actually after the training they remove the so you have backbone head. They remove the head and use these backbone features and compute the cosine similarity between the test and train images, and yeah, that's how the KNN classification works. And linear probe is just adding a linear head on that and training on this. But what they found is if you remove the momentum and center probe, it's actually losing too much. And another thing that they found is if you use cross entropy, also the loss, instead of cross entropy, if you use mean square error, the loss the performance is not that good. And also they also found this thing synchron, what is SK used in swab. Even if you use it here, there is no much gain. Actually there is no gain compared to this. In fact, there is a small reduction. So that is also the ablation they found here. And now we can see the results of the self-supervised results. So it's actually so if you look into the results, actually what one thing to observe here is so the linear and KNN. So if the KNN is having no training at all, so if you see between those two terms, there is no much difference in the performance. But if you look into using a WIT resonant backbone, it's actually a huge difference. So that in a way suggests that this is actually learning meaningful representation in the KNN space, in the representation space itself, and a simple KNN is enough to differentiate between the outputs. So I think that is all I wanted to talk about the Dino architecture, and I just discussed this paper, so I actually wanted to discuss Dino V2, which I will discuss in another video.